Halogens. All halogens molecules are diatomic and they form a single covalent bond between each other. So therefore, it's non-polar. Therefore, the intermolecular force that we have is instantaneous dipole to induced dipole attraction force. In terms of the color at the various state, it's actually in the data booklet, so you can see the colors from here. And color in the aqueous solutions as well, and color in organic solvent, like for example, your hexane. What I just want to highlight that iodine is very soluble in iodide. So in this case, the iodine and iodide will actually comes together. In this case itself, your iodide will form actually a dative bond with the iodine molecule, forming your I3 minus. And I3 minus is actually a complex ion and is brown in coloration. So the brown coloration is actually the presence of I3 minus. Oxidizing power of halogens. All the halogens on the standard electrode potential values are all FN species, and hence they are oxidizing agent. And the oxidizing power decreases down the group because the standard electrode potential value of your chlorine will be higher than that of your bromine, and bromine higher than that of your iodine. Chlorine, which has a higher oxidizing power, will be able to oxidize your bromide, and your bromine will be able to oxidize your iodide. So you can see that that's the displacement reactions that you learn at O-level. If we decided to dissolve chlorine gas into Ki, you end up with initially producing a brown solution. The reason is because of the formation of I3 minus. But however, as the amount of I minus is being used up, the concentration of I minus down here will decrease as well. So the position equilibrium will start shifting left. And that's the reason why, as you continue to add chlorine in excess, your concentration of I minus decreases, which means your solution will start to decolorize and you heat back to pale yellow eventually, because iodine exhibits a poor solubility with water, given the fact that iodine is a non-polar covalent molecule. And you will observe some black precipitate as well, and that is actually your iodine solid. So as far as the shape of I3 minus is concerned, it's actually your linear. You will know that the central atom is iodine molecule, as drawn here, and it has 3 lone pairs and 3 lone and 2 bond pairs. The 3 lone pairs will go into the equatorial side, so therefore the shape is linear. F3 minus unable to exist. The reason is because that our fluorine in period 2 is a period 2 element, so which means that it can maximum take up to a maximum of 8 electrons, since it does not have any D subshell. So the F minus is unable to do a dative to the fluorine atom because its outermost electron shell is really fully filled. Thermal stability of hydrogen halides. Quick introduction on hydrogen halides. H to X bond is actually a single covalent bond. X being the halogen, which is highly electronegative, so it's highly delta minus, resulting in H being delta plus. So the molecule is polar, and they are highly soluble in water to form an acid solution. In fact, when they dissolve in water, you find them ionizing to form H3O plus, NX minus, which kind of explains why HCl is able to dissolve in water better than ammonia, because the HCl would have hydrolyzed to form H3O plus and Cl minus, and they are able to do ion dipole attraction forces with water molecules, which render them to be more soluble than ammonia, since ammonia form relatively weaker hydrogen bonding with water molecules. So in terms of physical properties, HCl has got a lower boiling point, while HI has the highest. The reason for that, despite the fact that HCl has got the highest permanent dipole among all the 3 molecules, reason being that the electronegativity of Cl is way larger than that of your bromine and your iodine. Then why is it so that HI still has the highest boiling point? It's because HI has got significantly more electrons, and because it got more electrons, it has a larger electron cloud, better able to polarize its molecule with delta plus and delta minus, and therefore able to form stronger instantaneous dipole to induce dipole attraction forces between the molecules. So overall, the intermolecular force of HI is higher than that of your HCl. Thermal stability. Thermal stability and boiling point don't mix up, because thermal stability is looking at the chemical reactivity of your HCl, and typically you would chemically alter the molecule, which means that you will break the covalent bonds within. While in the case of boiling point, you're typically looking at the intermolecular forces between the molecule. So you're not talking about chemically altering the covalent molecule. So in terms of thermal stability, we will have to now look at the covalent bond. In terms of the strength of the covalent bond, certainly in terms of HI, I being a much larger molecule, meaning to say the bond length will be longer. And if the bond length is longer, the overlap of the orbitals will be weaker. And aside from that, your iodine is less electronegative than as relative to that of your chlorine. So therefore, because of this, we will expect the HI bond to be significantly weaker. While if you look at HCl molecules being smaller, so therefore the overlap between the orbitals are actually more extensive. And aside from that, the chlorine is a lot more electronegative than iodine. So therefore, it has a big delta minus on the Cl, while your hydrogen has a big delta plus. So the difference in polarity between the atoms result in Cl being more negatively induced and H being more positively induced. So the electrostatic attraction between them is stronger, and you bring the molecules closer, greater overlap. Therefore, the bond energy of H to Cl is significantly higher. So what does it mean if the bond energy is significantly higher? It means HCl is extremely stable, since it's very difficult to break the H to Cl bond. Relative to that of HI, which will be the bond energy between them will be more easily broken because of the lower bond energy. So in summary, what we have, when you go down group 17, the size of the atom actually goes up. The ease at which atoms lose its electron will actually increase because its first IE ends up as lower or less endothermic. And electronegativity drop as well when you go down the group. The bond energy decreases when you go down the group, with the exception of fluorine, of course, because fluorine has small atomic size that results in repulsion between the unbonded electrons and as well as the proton within both the nuclei. And finally, if you are better able to lose your electron more readily, since you have lower first IE, you're able to conclude that halogens will display greater metallic character, which is the reason why your iodine flakes looks a little bit shiny. When you go down the group, the number of electrons per molecule increases, so therefore the strength of the instantaneous dipole to induced dipole attraction forces increases. So the boiling point increases, the volatility drop, and the solubility drop due to the weaker instantaneous dipole to induced dipole attraction forces between the water molecules and the halogens. And if you relative that to the stronger intermolecular H bonds with water molecules tends to want to stay together. Finally, if you look at the reactivity of your halogen, it decreases down the group because then the electropotential, in fact, become less positive, all right? And therefore, because of that, when you go down the group, they become weaker oxidizing agent. And the reactivity with hydrogen would actually be less intense when you go down the group as well. Finally, let us take a look at the hydrogen halides. So we're comparing HCl to HBr and then to HI. So certainly in terms of Cl has got the highest electronegativity, and therefore the difference in electronegativity between H to Cl is significantly larger relative to that of H to Br and then H to I. So because the difference in electronegativity decreases, the ionic character of the hydrogen halide decreases as well. And when the ionic character of hydrogen halide decreases down the group, the covalent character of hydrogen halide increases. The net dipole moment, as explained earlier, that given the fact that Cl is more electronegative than Br, your net dipole moment of hydrogen halide also decreases as well. Number of electrons increases significantly. So therefore, the strength of the van der Waals forces, and van der Waals forces means intermolecular forces, which include both instantaneous dipole to induced dipole moment, and as well as permanent dipole to permanent dipole attraction forces. So in this case, the HI would have a stronger intermolecular force relative to your HBr, and HBr stronger intermolecular force relative to HCl. So therefore, the strength of intermolecular forces increases down the group for hydrogen halides, and therefore their boiling point increases. Of course, we have to leave out your HF because HF is able to form in strong intermolecular hydrogen bonding, which explains why it has the highest boiling point amongst all the hydrogen halides. Now let us take a look at the reactivity of your halides. Looking at the standard electrode potential values, you know that all the halides are the right-hand species. Because they're the right-hand species, they're reducing agent. Since they're reducing agent, and if you were to compare Cl minus to Br minus to I minus has a standard electrode potential value that is less positive, which means it has a better tendency for the reactions to go from right to left. And hence, because of that, we expect the reactivity of halides to increase because I minus would now be able to oxidize more readily. And hence, I minus is actually a stronger reducing agent relative to that to Br minus, and Br minus stronger reducing agent than your Cl minus. If you need to consider the thermal stability of hydrogen halide, we now need to look at the bond energy. As we kept earlier, we said the bond energy, if you go down the group, Hi has got the weakest bond energy. The reason is because iodine has the largest atomic size and it has also got the weakest dipole moment. Therefore, because of that, the bond length will actually, in actual fact, be longer. And so we expect bond energy to be less endothermic if you go down the group. And if the bond energy is weaker, the thermal stability decreases, which means thermal instability increases. And the thermal decomposition temperature will decrease as well. Thermal decomposition temperature for Hi will be the lowest relative to that of your HBr, and thermal decomposition for HBr will be lower than that of your HCl.